Okay, gang, we're back here with this time zone map, and just so we can tie it all together, um, time zones are often moved, if not in toto, at least maybe partially. So, for instance, a few years ago, um, Vladimir Putin took and folded a couple of places out here in the eastern part of Russia together to make from, 11 time zones down to nine, and then they switched it back again. I'm not sure why. Some countries like Iran and Afghanistan and India go on portions of hours, like at 30 minutes or 45 minutes of an hour. Those are local decisions. They can choose to do whatever they want to do. And this is totally different from looking at, a place like Indiana that decides not to use daylight saving time. That's up to them. But what it'll appear is that for during the standard time of the year, they're in the Eastern time zone. But when it comes to most of America flipping to daylight saving time, then they seem like they're in the Central Standard Time zone where we are, not East Tennessee. But anyway, why, you might ask, then, if they had this perfect geometric form of 15 degrees, 24 time zones, would they start messing and jogging the lines east and west, and in fact just cutting off time zones altogether? Look at this one right here. So this is a time zone that they jogged to the west, and this one here to the east, and they just clipped off that one in Russia altogether. But ask the question, who lives out here to care? This is Siberia. There's virtually no one out there, and those who are, it's kind of like living in eastern China. This is China right here. All the clocks in China are set to Beijing time. Beijing's right there. And most of those 1.3 or so billion people live within what would be considered a basic time zone. There's not a lot of people out here, okay? But that said, their clocks do read 8 o'clock in the morning just like theirs, but nobody's getting up at 8 o'clock out here. If the day starts at 8 o'clock, remember, China's as big as the United States. It'd be like someone in, San Francisco. The day starts at 8. But it's 7, 6, 5 o'clock. They're going to be at the office at 5 o'clock in San Francisco? No way. Okay? That's not how it's going to work. But that said, the beauty of the decision to make it based on the zero line of longitude here going through Greenwich, England, that 180 degrees over here gives you the international date line, and go in the opposite direction. You can see it on the other side as well. But pointing these things out is I think pretty important, that you know how these decisions were made and based upon what. So anyway, if again you're looking at this, just to understand that this is the motion of the Earth rotating on its axis. This is a 24-hour period of time. What we were looking back over here on I'll race you all the way back to the beginning. Sorry. With latitude, God, this is terrible. I'm sorry, I'm jumping around. But with 0 to 90, right here with latitude, that one has to do with the annual march of the sun as we go through our seasons of 365 and a quarter days. So this one is measuring revolution, that is around the sun, versus longitude's rotation on an axis. All right, I hope that's clear. I hope I didn't confuse you with that jumping around bit. But again, looking at the international date line, if you fly over and take a honeymoon in China, which is what we did, you lose a day because it's already the next day over here, and you'll never get that day back if you just stay in China. But if you come back, guess what? You'll get it back again, flying back and forth. So this was part of one of the issues that happened with Magellan and his crew. Only Magellan didn't make it back, nor did all but one of the ships and most of the sailors. But when they got back home again, after circumnavigating the globe, they had realized that they were a day off. So at some point you have to add or take away a day. And as they came from the Western Hemisphere into the Eastern Hemisphere, they should have added a day. This was also the crux of the book Around the World in 80 Days, a great book of adventure if you'd like to read Jules Verne. All right, moving on. Oh, by the way, we jogged these lines east and west in the same way. I didn't really fully make this out. You don't want these lines to run through a major city so that it's, on one part of the city, it's Mountain Time, and the other it's Central Time, or Central versus Eastern. You don't want that. So they move people, local officials and all, they move the lines to fit. Well, we don't want part of Alaska being wholly on a different day, so they jog the line east or west, depending on Siberia as well. And again, it's all of our creation, so it makes sense for us in how we do this. All right. In the text, too, there is this graphing this approach, the U.S. Land Ordinance, or Township and Range system that Thomas Jefferson put into play. If you've ever noticed a map of the United States and the configuration of the counties, the last two states to use the old meets and bounds English system were Kentucky and Tennessee. And so once you start looking at Ohio and Illinois and some of these places, they really have a grid-shaped format if you'll look at it from above. Okay, now I'm going to show you someplace out in in the Midwest, but looking at what was created here. So you had these baselines for building these 6x6 mile squares, and then breaking apart those pieces into smaller and smaller subunits. So in looking at this, I need you to see it both ways, coming out and going in again, okay? So with this particular box right here, they're saying this is our baseline, and that it's 1, 2, 3, township, 3 south. So they use township for, remember it's township and range, so this is latitude and longitude is what they're really referring to. So it's T3 south, township 3 south, and R range 2 east. So here's your principal meridian, so 1, 2. So I think you at least see how the baseline works. So going north of it would be 1, 2, 3, township 3 north is what that one would be. And if it's R2, it would still be R and 2 and to the east, but for that northern part there, north of that line. Okay, so if you look inside of that, then it breaks up into 36 6x6 in the area of it, into 36 distinct places. And so the counting begins up in the northeast, so 1, 2, 3, 4, 5, 6, and then you're here to the northwest. Then it wraps back. It's a snake, if you will, back and forth to get all 36 of these sections, they're called. Okay, so all of these 36 are sections of 1 square mile. Now, taking that, number 14, pulling that out. Now they're trying to tell you all about that 1 square there. Well, look at how you can make coordinates out of that. Do a cross through the middle and the middle, and then you'll have a northeastern, a southeastern, a southwestern, and a northwestern quadrant. And within that quadrant, you also have northeast, southeast, southwest, northwest. Okay, so when the address comes, it's the southwestern quarter, that yellow, of the northeastern quarter, this red line box here, to get you to the next part, which is section 14 of Township 3 South and Range 2 East. That is the mathematical address of that particular grid. Okay, so this is pictured very well on many parts of our landscape, you guys. So let me show you here. Well, I had that. So when you look out in certain places and you see it's all gridded off, you've flown over this country, I know you've seen this, okay? So I'm showing you this one here that I think I remember it being in Texas. I think that's when I did this. But I found an overlay within Google Earth that I could, it's called a KML file. So I got it to overlay to show you each and every one of these as you get closer and closer, okay? So as you go in, you can see how they're broken up and how everything is squared off, that the highways run along those squares, that they fit towns or farming area within those squares as well. And now this one is certainly a bigger view, a drawn out view, that these are all water wells out in Texas and Kansas, whichever place this is. I think it's Texas, but Oklahoma, Kansas, Nebraska, all of this is the Ogallala Aquifer. So all those circles, at the center of that circle is a well. So that said, you get closer and closer and you can see what's going on. Okay. But again, grid it off. Okay. This is by the Township and Range U.S. Land Ordinance. And that's what I wanted to convey to you. Okay, now how do we do stuff now that we have the technology? Well, we had satellites up during the Cold War, you guys, the Navstar system, and the government could, I should say, because it was built with our money. The government though could see all kinds of things around Earth about how to use to target missiles, or it was navigational. I mean, Navstar, that's what they called it, okay? So let me tell you real quick what's on every one of these satellites, and we're still using them, and Europe has a newer array, but these things are just incredibly accurate. Now, there are atomic clocks on those. So just as we talked about degrees, minutes, and seconds as distance, it's based on time as well. Okay, so each of these has an atomic clock. So if you have a receiver in your hand or in your car, the thing is going to send out a pulse, and it does not send out a pulse. I apologize. That's exactly what I didn't want to say. It receives pulses. Okay, so the time is calculated, triangulated with 4, 5, 6, 7 of these things above the horizon, and you receive where they are. This is how your how your driving voice will tell you, take the next right, and it knows exactly where you're going. Okay, it even has corrections for the time it takes for that pulse from the satellite to get to your car, so it corrects all of that. And so this is used in so many different things now. Before, it used to not be. We didn't know, for instance, how actually tall Mount Everest was until someone put GPS unit up there and measured it. And it used to be on old maps. If you'll look, it was 27,028 feet high. And now they knew it was 7 feet higher based on the use of real sophisticated GPS technology. Okay, so in understanding that, we end up mapping for this too. We use GPS. We use all kinds of data coming in, remotely sensed and otherwise, into powerful systems like computers, but beyond, for instance, necessarily the grid of, say, of a spreadsheet like Microsoft spreadsheet. It's just vast amounts of data through GIS then allows us to do all kinds of things about questions and answers about this planet. And even how they grade roads now. When you see a bulldozer like this and see these things on the top of it, that literally means that this dude is really just running the thing, but the satellites are telling how to get the exact grade that they want. He's not doing that. The information he's getting from the satellites are to how to get, whatever level landscape he wants. All right. I'm going to introduce real quick before I go to part 3 about maps, the advantages and disadvantages of them. But flattening them out, again, is problematic. So what I wanted to show you is we use larger and larger scale maps to go in closer and closer so we don't see as much distortion. So like when you say the shortest distance between 2 points is a straight line, well, that's very true within the room or across this campus, for instance. But if you get longer and longer distances, then you're talking about smaller Great Circle routes and stuff like that. So just a bit of editing here. But when we look at how Earth is depicted on flat maps like this one that's a planar projection, well, it's most accurate at the center because that's what was touching, say, the North Pole, but gets more and more distorted as you get to the edges. So then you might use a conical projection, which touches in the middle part of it and distorts, into a pinprick here and distorts around the edge, which would be the equator. But it all depends on what data you're wanting to represent. And so representing the data may choose, hey, I want a cylindrical projection. But I have to tell you that these are not very good either, because this one point at the top gets to be 25,000 miles across. The best part of the map is touching the globe at the equator and more distortion toward north and south. That said, though, why would you choose a particular map projection? Well, what do you want to see? How do you want to represent what you're looking at? Okay, all of these look like Jay Leno, I get it, but all of them were made for a specific purpose and are useful for whoever would choose to go with this type of projection. So I know it's a little weird looking, but there's endless varieties of types of maps and how to present information. And the way you choose them is to make sure they have the least amount of distortion for the thing that you're most interested in looking at. All right, come back with the final part of this lecture in just a moment. See you in a minute.